Hello, Chem students. Today we are beginning the gas law unit. Please take out your blue note packet and something to write with. The first concept we will talk about is the kinetic theory of gases. When we solve problems later, we want to look at gas conceptually to have a deeper understanding of what a gas is and how these gas particles behave. Obviously, we cannot see gas, so we have to have a way to think about them in a conceptual way. It's useful to set up a set of rules of how gases behave, and we should keep those in mind when we have to solve problems or do calculations later. This list of rules, expectations, and assumptions is the kinetic theory of gases. If a gas follows every single one of these rules, we can call it an ideal gas. In the real world, perfect and ideal are rare. We will almost always find a few exceptions to the rules. These exceptions are beyond the scope of this course. All gases we will be dealing with from now on will be assumed ideal gases. This theory states the following about gas behavior. Number one, gas particles do not attract or repel each other because they are very spread out. This is why they can be compressed so easily. Gas particles are flying around and they will not start clumping together. They are not attracted to each other. Likewise, they will not back away from each other. They will not repel. Number two, gas particles are much smaller than the distances between them. Most of the volume of a gas is empty space. This is why they have low densities, and another reason why they're easily compressed. Remember, density equals mass divided by volume. The gas particles that you normally see in glass jars and pictures are not scaled to size. The particles usually look like marbles. If gas particles were actually the size of marbles, the glass container would have to be the size of a football field. Number three, gas particles are constantly always moving and they move in a straight line. Number four, gases have elastic collisions. This means no kinetic energy or speed is lost when gas particles collide with each other or the sides of a container. Now, what is an elastic collision? Think about two balls of slime. These two balls of slime come together and hit each other. They're just going to splat. When these guys came together, they lost their kinetic energy. The speed and the motion that they had disappears in the collision. This is called an inelastic collision. A good way to think about an elastic collision is to think about two pink rubber balls. When they hit each other, they bounce right off. Or if one of those balls hits the side of the wall, it bounces right off. The kinetic energy is not wasted in the collision. The ball has the same amount of kinetic energy that it started with. This is exactly how you should think about gas particle collisions. They leave with the same amount of energy that they started with. Number five, all gases have the same kinetic energy at a given temperature. Gas particles move so quickly. At room temperature, gases have an average speed of about 1,000 miles per hour. As the temperature increases or becomes hot, the kinetic energy or speed of the gas particles increases. So the hotter it is, the faster they move. Therefore, temperature and kinetic energy is a direct relationship. One of the most obvious properties of a gas is that it exerts pressure on its surroundings. For example, when you blow up a balloon, the air inside pushes against the sides of the balloon, keeping it firm. Pressure is defined as force per unit area. We have the formula for that here. If you increase the pressure, you increase the force. Take a look at the picture on the left below. We have two containers with an equal amount of gas in them. Container A has low pressure because the gas particles have more space to travel. There are fewer collisions between each other and the walls of the container. However, if you look at container B, there is less space for the particles to travel, more collisions, and therefore more force exerted on each other, making it have a greater pressure. A larger scale of this is shown on the picture on the right. Atmospheric pressure. The Earth's atmosphere extends for hundreds of kilometers. This blanket of air is pushing down on us at all times. At sea level, the pressure is equal to 14.7 pounds per square inch. From now on, we refer to this as PSI. Pressure varies with altitude. The higher the altitude, the lower the atmospheric pressure. This is an inverse relationship. When you are higher on the Earth's surface, let's say like at the top of Mount Everest, which has an elevation of 29,000 feet, there is less of the atmosphere piled on top of you. In fact, the atmospheric pressure is just 4.9 psi. The air tends to be less dense. Less dense air means fewer oxygen molecules, making it difficult to breathe. You have to take in more breaths to get the same amount of oxygen as you would at a lower altitude like Galveston, which is at sea level, and it has a PSI of 14.7. Atmospheric pressure is measured with a tool called a barometer, invented by Evangelista Torricelli. Torricelli's original barometer was a glass tube filled with mercury inverted into a dish. Mercury flows out of the tube until the pressure of the column of the mercury is equal to the pressure of the air, or the atmospheric pressure, which is represented by the blue arrow below. If the atmospheric pressure is high, it pushes on the fluid, making it rise inside the tube. If the atmospheric pressure is low, there is not as much pressure exerted, and the fluid inside the tube will not rise as high. Mercury was often used in barometers. This is where the unit millimeters mercury comes from. But to honor Torricelli, the unit torr is used interchangeably. Pressure units and conversions. We have several different pressure units and conversions. Pressure units can look a bit strange. All of these abbreviations here are different types of pressure units. The most commonly used are PSI and atmospheres, or ATM. But you will also have inches of mercury, millimeters of mercury, torr, pascals, and kilopascals. Relationships between units are very important for conversions. You don't have to memorize them, just know when you see them that they represent pressure. Let's look at number 1. We have 0.50 atmospheres, and we need to find out how many kilopascals this is equivalent to. As always, start with the given 0.50 atmospheres. We're going to multiply that times the conversion factor between kilopascals and atmospheres. To find that, we will look at the box above, and we can see that 1 atmosphere equals 101.3 kilopascals. The units for our given atmospheres will go at the bottom, and our unknown, which is kilopascals, goes on top. And we do the math. 0.50 atmospheres times 101.3 kilopascals is going to give us 51 kilopascals. Remember, the atmospheres cancel out, and we're left with kilopascals as the unit. Let's look at number 2. We have 744 torr, and we're converting it to millimeters mercury. If we look at the box above, we have to look for the conversion factor between torr and millimeters mercury. We see that 760 torr is equivalent to 760 millimeters mercury. So we're going to write our problem. We're going to start with the given, 744 torr, times our conversion factor, 760 millimeters mercury, divided by 760 torr. Basically, 760 over 760 cancels out. So we know our answer will be 744. Our torr is going to cancel out. And so our unit is mercury, 744 millimeters mercury. Number 3, we have 17.9 psi, and we're converting that to atmospheres. If we look at the box above, we see that 14.7 psi is equivalent to 1 atmosphere. As always, we start with our given, which is 17.9 psi. And we're going to multiply that times our conversion factor, which is 1 atmosphere over 14.7 psi. Our PSI is going to cancel out. 17.9 is our given, so we're also paying attention to our sig figs. We have 3 sig figs here, so our answer will also have 3 sig figs. We have 1.23 atmospheres for our final answer. Okay, pause the video and you try problem number 4. Okay, we're back. Let's look at problem number 4. We have 155 kilopascals, and we're finding how many psi that is equivalent to. As always, we start with our given, which is 155, and that's 3 sig figs here, so we know our answer will also have 3 sig figs. The conversion factor between kilopascals and psi is 14.7 psi equals 101.3 kilopascals. Since we have kilopascals as the given, it will go at the bottom, and PSI goes on top. When we do our math, 155 times 14.7 divided by 101.3 is going to give us 22.5 psi. The last thing we're going to talk about today is temperature conversions. In the gas law calculations that you will learn, the temperature must always be in a unit called Kelvin. This is because the Kelvin scale is directly proportional to the average kinetic energy of the molecules. 0 Kelvin represents absolute zero, meaning there is no motion at all. There are two formulas that we will give you for temperature conversions. The first is Kelvin is equal to temperature in Celsius plus 273. The second one is degrees Celsius is equal to Kelvin minus 273. So let's look at our first practice problem. We're going to be converting 25 degrees Celsius to Kelvin. We're going to use the first formula, and we're going to add 25 plus 273, and we get 298 Kelvin. Our problem below it, we have 100 degrees Celsius. We're also going to use that first formula. 100 plus 273 gives us 373 Kelvin. Now we're going to do the reverse. We need to convert Kelvin to degrees Celsius. So we're going to look at this second formula. We have 300 Kelvin, so we're going to subtract 273, and we're going to get 27 degrees Celsius. And then our last problem, we have 273 Kelvin. We're converting to degrees Celsius, so we're going to subtract 273 from 273, and we get 0 degrees Celsius. It is important that you remember standard temperature and pressure, which is called STP before. It equals 273 Kelvin and 1 atmosphere. Okay, this ends our lesson for today. Please turn to your teacher for more practice.